Now that we know you are free to choose your point of rotation for a rigid body in static equilibrium, let's discuss why you might choose one point over another. So we want to construct our equilibrium equations for the body. The net force equals 0, indicating translational equilibrium, and the net torque about any point of our choosing also equals 0, rotational equilibrium. So we want to set up these two equations. We're still considering our beam here with points A, B, and C, and these three forces. So our task is to solve for those two forces, A and B. We want to know how much support each of these two posts is providing. What is the load on each of these posts? What is FA and what is FB if we place the beam here? Suppose we're given the mass of the beam and we're also given all the distances involved, the distances from each point to each other point. Yeah, suppose we know all the distances. In that case, our first equation, the translational equilibrium equation, the net force in the y direction, since there's nothing going on in the x direction, we just need to sum the forces in the y direction, and so that would be our FA plus FB and minus the weight of the beam equals 0. If we want to know force A and force B, we need another equation. There are two unknowns here. Only one equation, two unknowns. This translational equilibrium condition provides insufficient information to enable us to solve for those two forces. This one equation isn't enough. We need a second equation since we have two unknowns. What we're seeing here is that for a rigid body, it matters not just what the forces are, but also where on the body they are applied. We need an equation that takes into account where those forces are being applied. A rigid body is not just a point mass. The forces act at different locations, and those locations matter. This equation, translational equilibrium, doesn't take those locations into account, but the torque will. So we need at least one rotational equilibrium equation that tells the math where those forces are acting. So here's one option. We could take our translational equilibrium equation and add to it one rotational equilibrium equation. We could say sum the torques about point C. We'd let C be our rotation point, and if we're in static equilibrium, the net torque about point C should be 0. Indeed, the net torque about any point should be 0. So, okay, from our previous video, these were the three terms for our net torque about point C. There's force A, there's force B, and we see that we now have a system of two equations with two unknowns. It's solvable. We could now solve this system for those two forces. That's what we wanted. Okay, so that would work. But it's not our only option, and it's probably not our best option. Here's another way you could go. We could have that same translational equilibrium equation, but we could choose point A to be our point of rotation instead of point C. So if we imagined A was our point of rotation and summed the torques about point A, the nice thing is that force A exerts no torque about point A. So force A will not appear in this equation with the sum of torques about point A. We have two equations now with two unknowns, so it's solvable, but it's easier to solve because this equation doesn't have force A in it. We could solve the net torque equation directly for force B and then plug that answer back into this equation and then solve for force A. We'll get the same answer as if we chose this option here, but this will just be quicker to do the algebra. Okay, we have more options. In fact, I think we have the best option here. It turns out that we don't even need to include our translational equilibrium equation. We could instead write two rotational equilibrium equations, picking two different points of rotation. We could find the net torque about point A, set that equal to 0, and the net torque about point B, set that equal to 0. Get these two equations, and note that each one of them only has one unknown in it. We solve this one directly for force B, because force A doesn't exert any torque about point A. And then this one, we solved directly for force A. Force B didn't appear here because force B exerts no torque about point B. So that's convenient for us. We can pick 2 points of rotation, sum those forces, and solve relatively easily. In fact, that's our fastest option for solving for those 2 forces. We're always going to need 2 equations at least, but they don't necessarily have to include the translational equilibrium equation. Now, that could depend on how complex your scenario is. This is a simple rigid body supported at 2 points. If you've got a more complex body supported at more points, you're going to need more equations in general. Imagine now that we're modifying our scenario just a bit. Suppose that we hang an additional mass, M1, off the beam over here on the right-hand side. And we understand that if the beam is just resting on these 2 posts, that if this mass is heavy enough and if it's far enough out, the beam could start to tip at point B. If that mass is far enough out, the beam could sort of pop off of this post over here if it's not firmly attached to it, if it's not glued to it. If it could pop off and rotate about point B. So when would that happen? Under what conditions would the beam actually rotate about point B? At what point could it begin to tip? The clue is right here. If we've lost contact with this post, that means we have no contact force from that post anymore. We begin to tip at the moment that FA disappears. If we lose a contact force, then we're no longer touching that point over here. So I've labeled a few extra things in our diagram. I've shown D0, the distance from point B to the center of mass, and then D1, the distance from point B to the point where mass 1 is attached. Let's sum the torques about point B. We're going to get a clockwise torque due to force A over here, trying to rotate clockwise about point B. We're going to get a counterclockwise torque from this weight here, and then a clockwise torque from this weight over there. So there's those 3 terms. But tipping means that we're losing contact with A, so force A disappears. So we can find our tipping condition by setting this term equal to 0. Let force A go to 0, and we'll be barely balanced if that force A goes to 0. If this term disappears, we'll be barely balanced if that's vanished, if that term vanishes and the net torque equals 0. So if these 2 torques alone are balancing without requiring support from A, then we're barely balanced and just at our tipping point. So that then looks like this. The net torque about point B is just the sum of those 2 terms. The torques from this weight and this weight about point B. Okay, so we see that little g would cancel out here, and our tipping condition is that this distance times this mass equals this distance times that mass. And this is essentially just balancing a seesaw here, is what we're talking about. I would like you to notice, however, that this condition is identical to saying that the center of mass of the system, the M0 plus M1 system, this condition is identical to saying that the center of mass of this system is located at the support point B. Here's what I mean. If we set up an x-axis along the beam and set our origin at point B here, then we could compute the x-coordinate of the center of mass of our system from this formula. So the x-coordinate of mass 1 times mass 1 plus the x-coordinate of mass 0 times mass 0 divided by the total mass of the system. Well, x1 is just d1 and x0 is just minus d0. So if we set the numerator here equal to 0, that's indicating that the x-coordinate of the center of mass is at 0. In other words, that would be indicating that the center of mass of the system was right here at point B. So if the net torque about point B equals 0, and the system is barely balanced at B, that means the center of mass of the system is at B. So we're thinking about our tipping condition in terms of where is the center of mass of the system located. If our center of mass shifts over here to the left, then the system will tip and rotate that way. If the center of mass of the system is over here on the right somewhere, over here on the left somewhere, then our system would tend to tip this direction, but it'll bump into post A over here and be supported. So it'll be supported just fine if our center of mass is over here somewhere. But the moment our center of mass moves to point B, we're barely balanced then at point B, and if it shifts to the right of point B, we certainly tip.